Okay, guys. Well, welcome to the next one of my iPad videos. And today we're going to do double integrals. We're going to explain it. This is another like one of those things where a friend requested it, and I decided to do it. This is why I started my channel. On terms of where I'm recording now, I'm recording on top of a parking garage, and has a fire view. This is like Southern SoCal. Wait, no, Southern Orange County. And yeah, like we just admire the view. This is the iPad here, and like nothing like this and integrals. So yeah, have fun. But today we're doing double integrals. It's a pretty easy. It's one of the easier topics in Calc 3 or 2D if you're in UCI like I am right now. It's one of those things where it's easy to pick up as long as you remember your integrals. So let's get into it. So first we're gonna start off with a really basic one. Now in double integrals, I should note this. I should tell you guys this first. In single variable calculus, when you're integrating from a constant to a constant, a, b, f of x dx, f of x dx, you are really integrating, finding the area from like a line underneath a to b, and you find the area underneath the curve right here. That's what an integral is. But when you're doing it in the next step, which is double integrals, so let's say we have a rectangle, it's just going to be two constants, f of x y dx dy. Now, what is that? What that is instead of taking bounds from two one-dimensional curves, we're taking bounds from two-dimensional surfaces, and we're finding an area from that. No, not an area, a volume from that. So let's help you visualize that. Say you have this graph right here, this is in the x, y, z plane, and say we have this rectangle over here. It'll look like a parallelogram based on our reference frame, but it's a rectangle. So what we're doing when we're taking a double integral of f of x, y is we're looking at the volume under this function. So what I'm going to do now is actually going to draw something called a magic carpet. My old math teacher used to call it that. The magic carpet. You can imagine Aladdin on this shit. So what we're doing is we're looking at these two surfaces, which is this rectangle right here, and this cross sectional area of this magic carpet right here, and we're looking at the area beneath that, which is this cuboid looking thing or whatever it's supposed to be right here. We're looking at this area right here. What we're first going to do is learn how to integrate over a rectangle because a rectangle has is really easy to explain bounds because it's really two constants sandwiching each other. So for example, if you're looking at the rectangle, so x values are going to go from a to b and y values are going to go from c to d. So it's going to go like this: AC, BC, and BD, AD. Yeah, that's what this rectangle is. It's because rectangles are easy to learn because they are really just constants and not functions like you do in single variable. I will get, I will explain what I mean by like functions describing a surface later, but for now, just know that it's gonna be this. This is gonna be our starting point because it's just nice constants. Okay, so how do we do it? Well, it's kind of simple. So once we have our bounds, a to b, c to d, dx, dy, right? Because we are going, the x values are ranging from a to b, a to b. Our y values are ranging from c to d, and we're looking at the small area component right here, right? dx, dy. Find that small area component, and we're multiplying it by the height, which is going to be the f of xy at that point. F comma xy at that point. So this is how you typically do it. What this is the same thing as single variable, where if in single variable the equivalent is a to b of f of x dx. This is essentially looking at rectangles. So like this, you're looking at small components in dx. Multiply that with the height, which is f of x. That's our area approximation. It's the same thing. If you go back to that 3D magic carpet thing, it's the same thing we're doing here, except we're multiplying area components, which is this, and then we're multiplying it by the height at that point, which is f of xy. That's what we're doing. Now, how to compute this? It's pretty simple too. What you do is similar to partial derivatives that you learned at the start of the year. What you're going to do is you're going to like integrate with respect to x first, treat y like a constant, and plug in your x values. Then you do that with y. So let me show you an example to get it more concrete. 0 to 1, 0 to 1, x, y, dx, dy. This is an example to make it more concrete for you guys. So what we're going to do is we're going to treat y like a constant, like we do when you're taking partial derivatives, and we're going to integrate x. That's going to be x squared over 2. Y can be on the outside because it's a constant in this case. 0 to 1 dy. Now, if you plug that in, you get integral from 0 to 1 of 1 half y dy. And then you can solve that, you'd probably get 1/4. So this is how you do it. It's simple. All you got to do is you do iteratively. You do it iteratively, and you treat the whatever that's not the first variable as a constant. So in this case, y, and then you go on to the next one until you're out of dx's, dy's, or any d's. Right? That's how you do this integration right here. As you could have noticed, I tend to skip over the technical parts that you usually would learn in a class about like how these integrals work and why they're valid. I did that because, in my opinion, the double integrals over a surface, I think they're pretty intuitive. I think that's not why people trip up over them. I think I rather spend time on actual ways people trip up over double integrals. So in this case, I want to like focus more on setting up bounds. So okay, so how you do this? When you have a general region, right over here, and you want to find the bounds for this, what you need to do first is you want to look at what variable you want to integrate first. Now this can what that is depends on the actual problem. One way will definitely be easier than the other way in most cases. Sometimes it can just be the equally difficult, but most cases there actually be an easier way to do it. But you can use trial and error to figure that out. But first you want to choose which way you want to integrate. You want to integrate x first, so you want to do dx dy, or do you want to do dy dx? Okay, so if you want to choose which way you do it, you first look at the first variable right here. This is x, right? So if you're doing it x, you want your face to point in this parallel. You want your face to point parallel to the x-axis in this case. So if dx is first, your face points parallel to the x. So I'm gonna tilt my head 90 degrees. Now if we're doing y, we want our head to point upwards, right? We want our face to do it that way. So after you choose that, say I'm gonna choose dy because I like looking upwards. I don't like tilting my head. So for now we're gonna choose dy. You can choose dx, and sometimes you want to choose dx, but for now let's just make it simpler on ourselves and choose y. Okay. So what you want to do is you want to first check. Uh, what you want to do is first look at what functions this enclose this surface right here. So another way to think about it is say there's this function that you can trace around it that we can call y1 of x. And there's a second function right here that is y2 of x. So what you're going to do is you're going to look at this function, you're going to find those functions, and that's going to be a bounds. So let's say we have our integral right here, f of x comma y, dy dx. Our first bounds are going to literally be y2x, y1x. You're looking at the bottom bound is going to be the function that encloses the bottom half of the blob, and the top bound is going to be the function that encloses the top half of the bound. Now for x, it's going to be you're going to rotate your thing this way, and you're going to like look at the area like this, and then the area around this, and this is going to be a top, and this is going to be a bottom. But I think you guys can infer from based on how I explained it. So then for the second bounds, what the bounds for the second thing for dx, what you're going to ask yourself is what x value do these two intersect? Because they have to intersect two places if they're going to enclose an area. That's just like basic logic. You can think about it So you're gonna look at those 2 points and you're gonna be like, oh, what values are x at those 2 points? Say x is equal to a over here and x equals b. Therefore, you're gonna go from a to b. It's that simple. All you gotta do is just figure out which two functions enclose it, right? And then which two x values do they intersect at? That's gonna be your bounds. And now you're gonna have this function right here. So, and you're wondering, oh wait, now my bounds are functions. How does that work? Well, it's pretty simple. So you have a to b. Let's make it same thing, x y dy dx. We're gonna integrate it again. So when we integrate this, we're gonna have 0 1. Treat x like a constant. We're gonna have y squared over 2. Evaluate it from x squared to x of dx. So what we're gonna do is we're gonna treat x like a constant. Remember the function in this case, the function variable is y. So we're gonna plug into y's only. So we're gonna have 0 1. Oh, so minus dx, right? And then when we integrate this, we're gonna have x to the fourth over sixth minus x to the sixth over 12, evaluated from 0 to 1. And then when we do that, we're gonna have a 1/12, I think. Now the next step is understanding how we can change our integration components. For example, we have dx dy. Let's say that's a rectangular way of describing our dA. So this is going to be equal to dA. Remember? Now, remember we had dy dx. This is a rectangle. Say I don't like rectangles. Say I want to look at circular sectors instead. So it's going to be like this. This is a sector. This is curved. How do I find the microscopic area of that sector? Well, it's actually pretty simple. So we're going to look at this part right here. That is going to be a small change in the radius. So that's going to be dr. So what about this? What about this sector right here? Now, if you remember that the sector length is going to be the same thing as r theta if r is in degrees. But keep in mind, theta is going to be changing very small, right? There's only a small changes in theta. It's not theta, it's a d theta. So we're going to have actually a d theta here. So our small area component, in this case, dA, because if this becomes small enough, it's going to equal this. So dA, this is going to be r dr d theta. Simple as that. So say we want to, this time, let's say we have a circle. Now we could do it rectangularly. We can say, oh, the top half here, that's just if this circle's air length, the radius of the circle is r. So when we look at the circle called with radius r, we know that the top half, that's going to be r squared minus x squared. And if you look at the bottom half, that's going to be negative r squared minus y squared, no, x squared. Now, obviously, look at this. I don't want to plug that in and integrate that. That's going to be complicated. So one thing we can do is we can look at it from a polar perspective. So from a polar perspective, uh, this is actually equivalent to just two constants because our theta is going from 0 all the way around, to 2 pi. And our radius is going from 0 all the way to r. So in this case, it's going to be 0 to 2 pi, 0 to r dr d theta, and f of xy, where x equals r cosine theta, y equals r sine theta. Well, if you were smart enough to realize this is really a u sub in 3D, but we can get to the Jacobian and all that extra stuff later. But for now, you can know that this is just like a sub and a way to make our lives easier. Now, how do I make a blob? Now, you're thinking like, oh, what about just a normal blob in general? Well, it's simple. You have a blob right here. Now you gotta think about it like, oh, what r function in terms of theta is on the outside? Like if the origin is over here, what r function is gonna be on the outside, and then what R function is going to be on the inside. And then the thetas are going to be the relative endpoints, the intersection points between these R functions. So it's going to be theta 1, theta 2. So then we're going to have R2 theta of theta, R1 of theta, theta 1, theta 2 over dA, which is R dr d theta. That's how this works. Okay, this is all we have for now. If you are confused, uh, if I missed anything, because I did not make notes for this, if I missed anything or explained anything badly, let me know in the comments. I can make a remedial short or another video explaining more thoroughly. So yeah, have a nice day, y'all. Peace.